Hi everyone, this is your last video for Chapter 4. We're going to discuss how to build a calibration curve. Let's get started. Here I'm showing you typical data that you may obtain for a calibration curve. In class, we briefly talked about the purpose of a calibration curve, and now we're going to learn how to actually do one. Here I'm showing you data from a spectrophotometric analysis. In the procedure that they're using, they're measuring the intensity of color because the amount of color in the product that they're testing is proportional to the amount of protein in the sample, and that's what they want to find. Color is actually measured by the absorbance of light, which is recorded on the spectrophotometer. Now let's talk about the first row. The first row shows the blank readings. Okay, that's basically when there's no protein present, it's just a blank. And you notice that there are values in that row. It's not completely zero. And that may arise from the color in the reagents themselves that they're using for the sample prep. And what we call this a reagent blank because it basically measures the effects due to the reagents, not the sample itself. And then you have the preceding rows, which shows different concentrations of standard solutions. So they do 5, 10, 15, 20, and 25. And then, of course, they measure the absorbance of those concentrations 3 times each. So it's a triplicate analysis. Since your reagent blank actually has a measured value, you're going to have to take the average of that blank and subtract that average from each and every single one of your data points. So if you take 0.099 plus 0.099 plus 0.1 divided by 3, you're going to get 0.099. So you have to subtract that from every single data point. And that's why they have the second part of the table over here on the right where it says the corrected absorbance after subtracting the average blank. So if you take 0.185, which is this point right here, and subtract 0.099, you're going to get 0.0857. And that's how they get all of the different values on the right side of the table. You notice that there's a blank for one of the 15 microgram samples. And look at your 3 trials that you have for 15 micrograms. The first one is 0.392 and the last 2 are 0.345 and 0.347. Notice that 0.392 seems out of place. Everything else is pretty close to each other as far as the values, and that more or less seems like an outlier. And that's why they have this column here where it says range. You notice that the range of all the other trials are pretty small, but then when you get to that 15 microgram row, that range is super big compared to the other ones. So here I'm showing you the actual calibration curve if we were to plot all of the numbers that we had in our graph. Right away, 2 things stand out. The first one was what we talked about in the previous slide. You see that questionable point, if it was plotted, it would be right there. And you see that it's ridiculously high. And like I said before, it was about 4 times greater than the next greatest range, so they went ahead and discarded that point. The next thing you see is that all of the 3 points at the 25 micrograms all lie below the actual computed line. And they did a bunch of repetitions, and they showed that all of the repetitions consistently showed those points below the line. So what that means is that the linear range of this protein sample lies within 0 to 20 micrograms. So now to construct the actual least squares best fit line, they go ahead and they discard those 3 points from the 25 micrograms and that questionable point at 15 micrograms. So they're really only making it with 14 points, data points. And if you remember, they are going to construct that table that we saw in the last video where they find the xi, the yi, the deviations, the vertical deviations at every point. They sum them all up. They figure out what their slope is, what their intercept is, and what the uncertainties in each of those values are. It ends up being, if you do all of that, which actually I suggest you do, take the time and actually construct it yourself so that you get the same answers that they get for the slope, they get 0.0163. For the y-intercept, they get 0.004. For the standard deviation in the slope, they get 0.0002. For the standard deviation in the y-intercept, they get 0.002. And for the standard deviation in the vertical deviations, they get 0.005. So the final equation of the calibration line ends up being y plus or minus 0.005 equals 0.0163 plus or minus 0.0002 x plus 0.004 plus or minus 0.002. All right, so suppose that the measured absorbance of an unknown is 0.373. How many micrograms of protein does it actually contain? That's the easy part. The hard part is going to be what is the uncertainty associated with that answer that you give me. It's like I said, the first part's easy, so all we do is use the values that we've gotten for the calibration of the line, which is y equals 0.0163x plus 0.005, and all you do is take the unknown absorbance, which is 0.373, and you minus the blank. You always have to minus the blank. So that equals 0.274. Now you plug that in for y. So 0.274 is equal to 0.0163x plus 0.005. So the x ends up being 16.5 micrograms. Easy part. What is the uncertainty now? This is how you find the uncertainty in x. So really that should say S sub x. I forgot to put the standard deviation symbol there. But it is a little simpler in y. I hope you think so, because this to me is a little bit more complicated, and that's why I put eq. But this is the equation that you would use to find the standard deviation of a value in the x-axis. So it's sy, which is the standard deviation in y. We already figured that out when we made the calibration line doing the method of least squares. M is just your slope, but the absolute value of the slope, and then you square root it, and you have all these other values, which is 1 over k. K just happens to be the number of replicate measurements of the unknown. Your book gives you two examples. They give it to you as one replicate, and then they also on the side give you 4 replicates, so you can compare those two answers. And then n is the number of data points for the calibration line, which is 14 for the example that we did. Of course, you know what y is. Y bar is the mean value or the average of the y for the points on the line. So basically you're going to take the average of the 14 corrected y values. X sub I are the individual values of x for the points on the line. So for example, you had 0, 0, 0, you had 5, 5, 5, 10, 10, 10, 15, 15, 15, 20, 20, 20, and x bar is the average of those values that I just mentioned. Your book tells you that for a single measurement, of the unknown, k would be equal to 1, and if you plug in all those numbers to find the standard deviation in x, you should get plus or minus 0.38. So your final answer would be 16.5 plus or minus 0.4 micrograms of the protein. So that's how much protein there is in that unknown sample. If you actually measured 4 replicates, which is the other example they give you, you see that the actual uncertainty is reduced from 0.4 to 0.2. So your uncertainty actually gets better, obviously, because you've done more replicates. Okay, guys, this is it for Chapter 4. I want you to please practice how to do these and how to build these tables. Like I've told you already, you don't need to memorize these equations, but you do need to know what they mean and how to use them, because I more than likely will ask you a question concerning this and all the other things that we've talked about, the Grubbs test, the t-test, the f-test, all the other tests. Okay, so keep studying. All right, see you later.